Welcome. This is video 32 on torques, which torque is spelled up here, T-O-R-Q-U-E, and it's a turning or a twisting force. Uh, so you see this pretty often, typically with machines, and I snagged this picture here of the interweb so you could see one. This is, in particular, is someone who's trying to fasten two sheets together. I don't know what they are. But there's a bolt on one side and there's a nut on the other side, and the person is using a wrench to tighten that nut on this side. And you can see that this is the axis of rotation right there, and that they're applying the force all the way out there. And so even though the object is forced to turn right there, there's this force that's being applied pretty far away at some radius r away from the axis of rotation. Now, if this person wanted to, they could go ahead and rotate the wrench arm around in a circle all the way around and back to where they started again to be able to tighten this up. Typically, people don't do that with the wrenches, but you could, and you can see that it makes a circle. And so that circular path in which you were applying the force is the reason why I used radius right there instead of distance. Some people still use distance just to prove to you that they can, or just just because it's easy or convenient. I use radius because if allowed to, the object would move in a circular path. So it's important for you to remember that it's the radius of the circular path that it would take. Anyway, so I'm going to go ahead and erase that so that doesn't get in our way later on here. The question I would have for you is, where do we see torques? And quite frankly, we see them all the time. If we think about it, let's look at the wheel of a car. I'm going to draw a wheel right there. And so it has an axle in the center, like so. And that axle is, through a complex chain of machines, is connected up through to your engine. Your engine is providing a spinning force right there, and then it gets transmitted to the axle of the wheel. Now, what's happening is that the turning that comes out of the engine is actually being applied to the wheel right here. And as a result, the axis of rotation is right here in the center, and the whole wheel spins. So the whole wheel is spinning around like so. This is not anything new, but what you haven't maybe thought about is this. What actually happens to get your car to move forward? Well, if you think about it, the road surface is here. The wheel is spinning around that location right there, and the force that the wheel applies to the ground is right here on the rim, like so. So there's a force there, and it's at this radius away from the axis of rotation there. And so you can see that all of a sudden now we have a force that's not being applied at the center of mass anymore. We have this weird situation in which we have a radius away from an axis of rotation that a force is being applied. Whenever that happens, we have a torque. And so there's a couple of here I just drew another wrench situation to outline some of the terms that may come up. So the first one is axis of rotation. We've talked about that a little bit already. It's the either natural or forced place in which an object will rotate. In this case, we forced it to rotate around this, whatever that location is right there. Let's say it's a screw or a nut that we're trying to put into, or we're trying to use to fasten things together. We might also call it a pivot if it's an object, or an axle even, if it's an object like a wheel, where it can rotate around a central point. Pivot also is used for levers. So if we have a lever situation like so, where we're trying to lift up a box, so here we put a box on the short end here, and then we apply a force to the long end right there, and it's easier to lift up the box. This thing right there would be called the pivot. That's the place in which the lever is forced to rotate. Now, typically the center of mass of the lever and the weight would not necessarily be right there, but they could be. But that's not the point. The point is that we put the pivot where we want it to rotate. We don't have to use the center of mass anymore. We also have this distance right here, which is a vector quantity, so it's almost like a displacement, which we call the moment arm. This moment arm is the distance away from the axis of rotation that the force is being applied. So we know it's some distance away from the central axis point. And then, of course, we got the applied force. Now, when you put those two things together, when you multiply them together, you end up with our formula 5.1, which is right here, which is the torque. This is the measurement of the torque, is equal to the radius of the moment arm right there, multiplied by the applied force. When you multiply those two together, you end up with this number, and that gives you the torque. Now, the units, as you might imagine, forces are in newtons, and radii are in meters, so the units end up being newton meters, like that. And there's no nice, easy, abbreviated way of talking about it. We just use newton meters. Now, torques are kind of interesting because they highlight the fact that it's not just the amount of force that you can apply to be able to get something to move. For example, one of my first memories was being in my grandpa's garage, and my grandpa had a bunch of rusty old stuff, and I don't know what he used to do with it, but occasionally he would try to take it apart and put it back together again, maybe clean it off. Well, one time I remember he had this bolt, and this bolt was a hex head bolt, just like I drew right here. And he put a wrench on it, and he pulled, and he pulled, and he pulled, and it didn't matter how much force he was able to apply, he could not produce enough torque to be able to get the bolt to move, the bolt to rotate. He could not change its rotation against the force of friction. Bolts, because of their screw threads, actually have a huge amount of friction. That's why we use them to fasten things together. But they also can be super annoying when they get all stuck and rusted together. And so that was the problem he had right there. Well, all of a sudden he goes into the garage and grabs a huge pipe. And that pipe was just a hollow pipe, like you might imagine. And he stuck it on the end of the wrench. And instead of turning the end of the wrench, now all of a sudden he took his force, the same force that he was applying before, and applied it out here. Now look at, obviously the forces are the same, so he didn't change the amount that he could apply the force, but what he did change was the distance it was away. So you can see it's a much, much, much bigger radius rather than that tiny little radius right there. And because he increased the radius, he was actually able to turn the bolt as a result because he could produce enough torque. And so we're going to explore this concept of torque in class through a couple of activities over the course of the next few days. Now, one of the things that you're going to need to know for torques is this thing called the right-hand rule. You don't really need to know the right-hand rule itself, but you do need to remember that counterclockwise torques have a positive value, and clockwise torques have a negative value. And the reason for that is that we just decided that's the case. We wanted to give them a value, and you're going to see why when we talk about rotational equilibrium in a little while. But I wanted to point out to you why that is the case. So I have here a right hand of someone that someone drew better than me, right? The right hand that this person drew has the thumb extended. And so you can see the fingers curl around. Now, as an interesting point, if you look at it, if the thumb is pointing at you, the fingers are curling around in a counterclockwise direction. And so if the thumb's pointing at you, that's positive, and that's counterclockwise. If you're looking at the bottom of the hand here, you're going to see the fingers curl around in the clockwise direction, and that's pointing at somebody else, and that's negative, so your thumb would be pointing at somebody else. Just to prove to you what that means, so you take your right hand, right, and you curl the fingers around. Now I think you can see that from your perspective, you can't see my thumb, it's pointing at me, but from your perspective, those fingers are curling around in a clockwise direction. If I could turn it around, you can see that the right hand here, my fingers are curling around in the counterclockwise direction, and now my thumb is pointing at you. and that would be positive, negative, positive, and negative. I hope that works. I'm going to assume that works. All right. So we're going to use that information to be able to answer some questions and do some activities in class, particularly using levers. So hopefully that makes sense. If you have any questions, please let me know. Thanks for watching.